Good morning, everybody. This is a very cozy crowd that we have here today, but let's see what we can do here. My name is Niko. I'm the CEO of ICSI, and I'm here today with Harri, who will help me out with the presentation. We founded ICSI 4 years ago, and we are a startup based in Finland. Today we are 70 people working dedicatedly and fully only on figuring out what could be the future and the next generation of eyewear. When we started off, we had 3 questions that we wanted to answer. And these 3 questions were, of course, can we do a new way to fix eyesight? So what we have come up with is a dynamic, fully tunable lens. The second question was, how can we do a functionality that allows you to just put on the glasses, not having to worry about pressing any buttons to change that lens? So we talk, how do we do autofocus? And we started off by forward-facing sensors, time-of-flight sensors, trying to figure out what is in the environment. But the problem, of course, is when you have an outward-facing sensor, you can still keep your head steady and you can move your eyes. So it didn't really work. It gave a rough estimate of what a person is looking at. So we came up with a new way how to do eye tracking, and with eye tracking we can figure out the distance what a person is looking at from the convergence of the eyes, which works for the majority of us. And then the third big problem or question that we had was, can we actually pull this off in a form factor that resembles pretty much identically eyewear? So standard eyewear that we know today, eyewear that nobody would actually recognize that a person is wearing something completely new. And let's dive a little bit more specifics into these 3 topics, and hopefully we can also pull off some demos for you. If we start about the lens, this was of course and obviously the biggest question that we have here. And what I have here in the background is quite a cool video. This is liquid crystal behaving kind of badly, but it was a very impressive footage. It's very hard to capture actually liquid crystal. And liquid crystal is quite interesting. It has been researched for many years. Most of us know it from different type of displays, originally from the Casio calculator displays, where liquid crystal was a very nice way with very low power actually to create numbers. We are using it quite a bit more sophisticatedly. So we are using liquid crystal in a free-floating, very thin layer. And we have an electrode structure with an alternating current. We can actually turn liquid crystal slightly differently at different positions, and this way manipulate light. And with our electrode structure and the liquid crystal that we have selected, we can create a waveform that resembles a traditional lens. So what we have in a sense is a very thin lens that we can change power with a relatively simple electronics that actually fit into normal looking eyewear, that uses very low power and has already a very usable diopter range. Why don't we try, Harri, whether we could pull off a small demo here. So what we have here in this setup is we have a camera and we have a target. And the camera is in manual mode, so there is no movement here on the camera. And of course the first use case is that we start to have trouble seeing close. So if I move the target here, it should become a little bit blurry. Yeah, looks good. Then I'll take a lens. And as you can see, it's really a lens where there is pretty much no power. And I'll just put it in front of it. There is absolutely no help from this lens. And Harri will take the mobile phone that controls the lens. Harri, can you give me a little bit of plus power? right. So now we have a lens that actually provides us magnification. Can you, Harry, turn it on and off a little bit so that we see the speed? That's on, off, on, and off. Great. And the lens is very nicely transparent. It's only 0.7 millimeter thick. We have 2 layers of liquid crystal, one for each polarization axis here. And the range, as I said, starts to be quite usable. But let's see if I can pull off a party trick to provide you a little bit more dynamics. So we go back to the normal situation, we are seeing okay. But what if we put it a bit further out so we can't see far enough anymore? And the lens obviously doesn't really help here. But Harry, if you give me a little bit of minus power. There we are. So now we have minus power in the lens. Can you turn it on and off a few times? Yeah, just go ahead, on and off. All right. So we have here a lens that we can dynamically change to any tune. It's not just an on and off lens, but we can also tune the lens to multiple different powers. And this lens that I have here is our older generation. It has a little bit of extra haze. I have here a lens that we made actually on Thursday, and this lens has half the haze, and the transparency is already 93%. So from a lens perspective, it's been a super interesting journey. And when we started off with these lenses, we were using the same manufacturing process as everybody else in the industry. We were using liquid crystal factories, which are usually based on chemical etching. So there is a mask of the electrode structure which is being etched onto a substrate, usually some sort of large plate. And what you see here now in the background is actually one of our lens parts, which has the electrode structure in it. Without any liquid and without assembly, it looks like a tiny CD disc. It's actually pretty cool. And we came up with a maskless manufacturing method. We asked some help from Fraunhofer Institute in Germany. Then we worked together with the University of Jyväskylä in Finland. And together with them, we came a completely new maskless way how to produce the electrode structure with femtosecond lasers. And for us, this was really the ticket to a breakthrough. Instead of having to wait 2 to 3 months for a new lens generation, we can now make these lenses in 24 hours. So if we have an idea, we can have a new lens in 24 hours. And this really changed the ball game for us, because now we can iterate extremely fast. And as I said, every week we seem to have a small steps change improving the lens. And we will just continue on this journey forward. So this is super cool at the moment where we are. If you, Harry, also kind of show a little bit the next slide, yeah. So we have, and the lens that I showed you had 26 millimeters in optical diameter. And the reason why we have picked 26 millimeters is the fact that people have eyes in different positions. So we have to move the lens, of course, to everybody's optical center. And it would be nice to have a bigger lens, but then we would actually be hitting the edges of the frame, and we wouldn't be able to do the optical range that is required for a fit and function. So if I can repeat a few stats, we have a lens that is 26 millimeters. We can position it very freely anywhere around the glass. We can freely tune it. We can do plus power. We can do minus power. So this lens, for some people, can already be the only lens that they need to have in their glasses, and they can adjust the power on the fly. But that type of lens, of course, has a very limited use case. So our first generation lens, we will be packaging with a traditional lens together. So you can imagine that we will be sandwiching this lens inside a traditional lens. And in the beginning, this traditional lens will provide a single power, completely unobstructed, regular single power field of view. And then when there is a need for an add-on power, based on the autofocus functionality, we can turn on the add-on power automatically. So it's a new generation of progressives that we will be launching soon. And in order to do the packaging of the lens, we announced actually yesterday that we have purchased Finland's last remaining optics manufacturing line. So we call it now IXI Optics, and we have now full capability to freeform traditional lenses so that we can actually innovate in the packaging of the liquid crystal with the traditional lens. And we have partnered up also with OptiSwiss, the largest independent lens manufacturer in Switzerland, to ensure that we can ramp up the volume production as well. All right, so that was the lens part. Let's switch over to the second part, the autofocus. And as I mentioned earlier in the speech, we are doing the autofocus part with eye tracking. And if I repeat one more time, how do we and why are we using eye tracking? It's very simple. So we're using the convergence of eyes. If I have a vector of both eyeballs, and you look at something that is close distance, for the majority of us, our eyes converge. And from this convergence information, I will know the distance a person is looking at. I know whether a person is reading, using a computer screen, or looking far into the distance. And from this information, I can use in order to control the lens completely automatically. So every time you look at something close distance, you get the add-on reading power. Every time you look further out, it disappears, and you have the traditional lens only. And eye tracking, of course, has been researched for a very long time. We have here a few gentlemen from Tobii who are the pioneers in eye tracking. I have also been involved in making one eye tracker, and usually these eye trackers are made with cameras. So there is a camera that is capturing an image of your eye. There is some kind of illumination system that creates and illuminates the eye, usually in IR spectrum, maybe even dots that we usually call glints. But the problem with this type of eye tracker is that you have to take 60 frames or even more from both eyes continuously. And having a computer that can actually take in and process 60 frames per second requires quite a lot of compute and power. And of course, integrating cameras into this type of form factor is not very easy. So we came up with a new way how to do eye tracking. And with our eye tracking, we are using the eye in a slightly different way. I have one explanation how to explain how the eye tracker works. Our algorithm guys, they don't really like this explanation, but I think it's a logical way how to understand how it works. So if you think of a cat eye or a reflector, and I rotate the cat eye and reflector, the intensity changes, right? That's why it's called reflector, so it reflects light. Our eye has a pupil, which is a hole, so when the eye rotates in respect to the frame, the reflection fingerprint or how the eye reflects back light changes. So our eye tracker works in a way that we have very short blinks of IR spectrum light, and then we measure the reflection intensity with photodiodes. Very simple components, very easy to integrate into the frame. And the most important thing is the eye tracker is extremely low power. I'm wearing frames that have the eye tracker embedded, so these are actually our frames that we're planning to produce. Let's see if we can pull off a demo here. So my glasses are now connected to that tablet over there that Harry is beaming to the screen. And if I rotate my eyes, you can almost imagine my eye rotation from the signals that we are showing here. And this is raw data. This is just raw data coming from the signals. So let me see if I can rotate my eyes a little bit. You might see some rotations there, or can imagine some rotations. Harry, can you show me one sensor signal? So I'm keeping my eyes steady and doing nothing. And then I blink. And you should see nice blinks, yeah. I'm keeping my eyes steady again and blinking. And let's show the actual eye tracker. So This is again my combined vector of both eyes. And I'm rotating a little bit my eyes, and you should see the vector. Now I'm looking at the screen actually. That's a bit slow. Yeah. Anyway. And at the bottom of the screen you can also see a more sophisticated signal. We are multiplexing some of the LEDs and photodiodes here, so if I blink with one eye you should see the signals go quite high, the other eye. So with this eye tracker that we've built, there is one more party trick here. I have not calibrated these glasses for weeks. I put them on and they start working. This is something I call persistent calibration, and if you have been using VR headsets like Apple Vision Pro, you usually have to calibrate something every time you use them. But this would be very inconvenient with regular eyewear. So the target here is you put on the glasses, you start your day, and things just start to work automatically. All right, let's continue on the third topic of can we actually integrate everything into a frame that looks like a traditional frame. And in order to do that, of course, everything needs to be very, very low in power. We need glasses that work with you the whole day, which means that these glasses can't really use any power. We also want to make glasses that look like traditional glasses, which means there can't be much electronics. We can't carry a computer with us. We don't have the compute required to run cameras. So these glasses are completely camera-free with tiny microcontrollers, very little memory, and very tiny batteries. The batteries that we are using are actually very similar to Apple AirPod batteries, those ear things that you can use to listen to music. Those batteries in that size format are now quite readily available, and those are the batteries that we have integrated into the temples. With smart glasses in general, if you walk into a store, you run into a problem. Eyewear customers are used to having a huge selection of designs, forms, ergonomics. And you usually go into a store and you pick roughly a frame that you like, and then you try it on. And if it doesn't fit, you continue and try on the next one until you find a combination that fits and looks great. With smart eyewear, you can't really do that. We don't have the luxury of making 100 different designs because we have to integrate the electronics into these glasses. We can't make 100 different forms with different heights of the temples, angles of the temples, different nose pads either. So what we need to do is we need to come up with a timeless design that we can vary as efficiently as possible. But most importantly, we have to design frames that actually can be made to fit for the majority of us. And this has been actually a huge, huge challenge. And if you walk around here and look at the smart eyewear, think about this. How much can you actually customize the fit of these frames that you see there? We took a completely different approach. First of all, we measured hundreds of people in different countries to understand how do these frames fit. And there was this really one big difference, eye related to nose height, which kind of screwed up our original idea of how do we manage the pantoscopic tilt. So we had to redesign the hinge completely so that we can actually adjust plus minus 5 degrees in order to have a perfect ergonomic fit. This is very difficult to pull off if you have electronics in the frame and you have cables going through the hinges, but we managed to do it. A second part about the temple is that we didn't put any electronics into the temple. We have only our tiny batteries. And the tiny batteries are only in this position here. So from here onwards, our temples are completely empty, and we can still bend them with heat, as is the custom with existing eyewear. So this is another pretty cool feature. And most of the volume in traditional eyewear is actually in the front of the frame. So this is where we have the electronics. I have my compute unit here in the nose bridge. My eye tracking sensors at the sides of the lenses. My display driver, sorry, not display, but my lens driver for the tunable lens is here in the corner. And then we have a very nice hinge that also serves as the charging port. And this way we have a very nice adjustability for fit from the temple perspective. Another important area, of course, because the contact points are basically ears, the side of your face, and the nose, is the nose pad. And our frames are these traditional plastic frames, because that's where we hide the electronics. So the first version of our glasses had only nose pads in the traditional sense. We did do one trick, so we will be offering these nose pads in different thicknesses so that the customer can actually change these nose pads and vary them and find a distance that works. But this wasn't good enough. Again, doing testing, if the nose shape doesn't fit, it doesn't fit. And we do want to have every customer that is interested in our glasses. So at the point of sales, we can actually customize our glasses, and we will be offering also traditional nose pads with a wire so that they can be bent and have more traditional fit. This looks slightly funny because we are not used to have glasses with traditional nose pads which are plastic, but for some people this is totally essential. All right, so I gave you a snap peek of the technology that we have invented. So we have a tunable lens that we can change. We have embedded all the electronics and eye trackers in a frame that actually looks and feels like a traditional frame. And we have embedded all the electronics in this form factor. We will be talking more about the frame and the product. We are not yet launching the product, so this is just a sneak peek of the technology. So hopefully we will be here next year and you will be able to hear more of our progress. Thank you very much, and if there are any questions, feel free.
Thank you. I had a quick question about the power range you can access right now and the power range you want to access in the near future.
That's a good question. So the question was really about the power range and how much optical power we can do with the liquid crystal lens. We are not yet announcing the power range. We haven't decided what will be the final power range. And we will be mainly offering the first generation from 0 to plus, because we want to do add-on power for progressives in order to help on the reading and near-distance reading use case. In the lab with single layer liquid crystal, we can currently do up to 2.5 diopters. It's not about the question how much power we can do today, because we can stack more of the liquid crystal layers. I can stack 2 of the lenses, I double the power. So currently 5 diopter swing is something we can easily do with 1 liquid crystal layer, but we continue improving on the structure and how well we can manipulate the liquid crystal. When we started off, we were doing lenses with a maximum power of 1 diopter, and we thought that's the maximum. Today, we have pushed it to a much bigger lens, to a much higher diopter. So let's say where we end up with. But the only point of doing these type of glasses is if we can offer a reasonable range of power. Otherwise, it doesn't make sense.
It's very impressive. Do you see there being a market for people, even if they don't need vision improvement, for cognitive load or other measures based on the metrics around eye tracking and blinking, etc.?
Yeah, that's a very good question. We haven't seen ever an eye tracker that you could wear in something that would look normal. And for the first time, the frames that I'm wearing, they look normal, and we can measure continuously eye tracking. We run these glasses at 60 Hertz when we want to have information, but with this hardware and with the components that we have, we can run up to 1000 Hertz. So we can really get micro movements of eyes, but the power consumption goes linearly up, so we really don't want to do it. And when the eyes are not really moving, we slow down the eye tracker in order to conserve power. But of course, blink information is something which is hugely interesting. So Harry, maybe you can, do we have the screen? Okay. Do we still have the tablet? Harry will show my blink information and some other interesting data that we've been collecting while I've been speaking. So of course we can collect continuously data. Also, what I mentioned yesterday when I was at the SILMO Next stage, because of the eye tracker, we understand also when a person is able to focus. When you're trying to look at something and you're trying to focus, but not being able to focus. Maybe your eyes are tired. Maybe you need an extra amount of power. That's something we could do automatically as well, on the fly. Or you could have different profiles for morning and for the evening as well. So that part is interesting, but there's loads of stuff that we can get from eye movements because eyes are connected to the central nervous system. And this is a completely new platform to gather health or medical related data as well. We are currently not pushing very hard on the medical and health front. First, we want to finalize these products. But when we have the product out and people start wearing it, it will be an interesting platform for this type of medical and health data. All right, so here we can see my blinks. My current interval is quite fast. My average has been 2.3 seconds. Yeah. I have 0% of either focused or daydreaming. And the reason why I'm saying either focused or daydreaming, because if you're super focused, your blink slows down. If you're daydreaming, your blink slows down. And that part is a bit hard to distinguish which one is it. So that's why we have here both. Of course, my blink rate would change if I have dry eyes and I start to kind of have trouble with my eyes because they're getting dry. So you could use this type of frame also to collect data for that. So do you need eye drops? We could maybe provide a message there. Also, the reflection of the eye changes when you put in liquid. So there's also a chance that we could maybe actually also check whether a person has been taking their eye medicine as needed. So there's a lot of stuff that you can do with this type of product. Harri, do we have any other data that you could show to us? All right. Yeah.
Oh, yeah. We do have the accelerometer inside the glasses as well. We need to know when the data coming from the glasses is actually reliable, because when you're driving a bike on a cobblestone road, you don't want it to change accidentally because your glasses are jumping. As a side product, we do get these sort of balance sort of things. But for us, probably the more interesting part is the posture. So we basically know that now that Niko has been talking, his posture has been quite good. The 45 degrees up is because the glasses were on the desk for a while. Ooh, sorry, there's something on top of it. There we go. So Niko has been having a quite good posture. It's not the sort of the nerd or the text neck syndrome going on so far.
Well, let's see if I'm using my mobile phone, and maybe you can start to see that I'm collecting. Yeah, the red bar is where it's not supposed to be, so I'm really putting a load on my neck here at the moment. We are basically only using an accelerometer in the product to do this. Initially, the accelerometer was used to help on the calibration of the product, but we decided to leave it in because it's information that is actually quite interesting. And using a mobile phone and straining your neck by looking downwards is obviously not a great thing. And these glasses can provide you a very easy way to measure that type of behavior. All right. Any other questions? That was a good one. Thank you. All right. In that case, thank you for coming over and listening to our speech.